Okay, problem solving for 1.8. Like I mentioned, this should be a relatively short video. We're going to just do these 4 example problems, which don't take super long, so you can expect this to be 10 minutes or less, I hope. First 2 problems we're going to do are going to ask us to name compounds, and then the third and fourth problems are going to ask us to do sort of the opposite. We have the name, and we're going to be trying to determine or write the formula for it. So in problems 1 and 2, we have the formula and we're going to the name, and in problems 3 and 4, we're going the other direction, right? We have the name, but we need the formula. So let me go ahead and move things over to the document camera. I've already written these problems out, and we're just gonna knock them out. Okay, so we need to name the compound Li3N. Okay. Well, important thing to note, names of ionic compounds are always written in the form of cation and then anion. Okay, so the cation comes first, the anion comes next or last. Cation is the positive ion, anion is the negative ion. So let's make sure that we know which one is which here. Well, if I take a look at my periodic table, which I hope I have handy, I do. Okay, here's lithium. It's in group 1. It's got 1 valence electron. It's going to lose that valence electron and adopt a positive 1 charge. Okay, so lithium would have a positive 1 charge. By the way, that's how you write positive 1 in chemistry. It's just a plus sign. You could write 1 plus, but I wouldn't recommend it. Okay, so anytime you see this with just the single plus sign there, that means positive 1. Okay, and we have 3 of those, right? Okay, and then I have nitrogen. Well, let's take a look at nitrogen. Nitrogen's here. Nitrogen would have, let's see, 1, 2, 3, 4, 5 valence electrons. Okay, so nitrogen could take 3 additional electrons, giving it a -3 charge. By the way, that's how it's written usually. It's usually written 3 minus rather than -3. If you write it -3, that's not really wrong. It's not a huge deal. I'm just trying to show you guys what's typical, okay? All right, and we have just 1 of these, right? So just the 1 nitrogen. You can see here how the ionic compound is electrically neutral, right? Overall, it has a negative, or overall it has a charge of 0, right? Positive 1, positive 1, positive 1, -3. They balance each other out, right? But what would the name be, right? So I've sort of done a little bit more work than you actually need here. Well, these are the cations. This is the anion. You don't actually have to refer to the number of cations. It's easier than that. You can just say, oh, this compound would be called lithium. Okay, now this is the element nitrogen. Only thing you got to remember here is that anions get the suffix IDE. Okay, ide. It's going to take a little bit of time for you guys to learn what these different anions are. This is lithium nitride. Okay, so it's not nitrogenide or nitrogide or anything like that. It's just lithium nitride. Okay? All right. Let's take a look at the next problem. Name the compound TiS2. Okay, well, let's look at where those different elements might be. Here is titanium. Uh-oh. This is in the transition metal section. Okay? You cannot use the periodic table or the patterns on the periodic table to determine what the charge of that is going to be. Okay? You cannot do that for transition metals or the lanthanoids and actinoids down here. Okay? You can for the main group elements, which are group 1, 2, 3, 4, 5, 6, 7, 8, right? The main group elements. So let's not talk about titanium just yet. Let's look for sulfur instead. Okay, so sulfur is here. 6 valence electrons in this column, meaning sulfur could take on 2 additional electrons, resulting in a -2 charge. And we have 2 of them. right? S2. So each of these has a -2 charge. What that means then is that we can determine what the charge of this would be, okay? Because all ionic compounds are electrically neutral. They have an overall charge of 0. Therefore, this one titanium ion must have a charge of +4, okay, to counteract the two -2's. And then its name, right, titanium is the cation, so this would be called titanium. Now, remember, for these elements here in the middle, okay, transition metals, and then honestly, these guys as well, all right? So like group 4 elements, carbon, silicon, germanium, tin, and lead. I talked a little bit about in the other video how these guys, it can be hard to predict their charge as well. And then obviously for these guys down here, we have to use Roman numerals. Okay, so if you can't use the periodic table to come up with their charge, then you have to use a Roman numeral. All right. Okay, so then this would be titanium 4 sulfide. Okay, because sulfur would change to sulfide when it gets that "ide" suffix. Okay, so there we go, titanium 4 sulfide. Okay, now we're going to be doing the flip side here, right? We've got names, but we need to come up with formulas. I like this a bit better. Okay, so we have aluminum and oxide. Okay, well, aluminum must just be the element aluminum. I'll leave it at that for just a second. Oxide, well, I noticed that this ends in "ide," which means it's probably talking about what? Oxygen, okay? Now, you have to be a little careful. There are some polyatomic ions that do end in "ide, but most of the polyatomic ions do not. Okay, most of them end in "ate" or "ite" or potentially something else. Okay, but rarely do they end in "ide, but some of them do. Okay, so you just have to be a little bit careful. If this had said aluminum peroxide, okay, so peroxide actually is one of those polyatomic ions. It's O2 with a -2 charge. Then you would just use this ion, okay? But because this just says oxide, this is only talking about the element oxygen. I can consult the periodic table to find its charge, along with aluminum. Okay, so here's aluminum. It's in the group that has 3 valence electrons, meaning it's going to lose those 3 electrons to adopt a +3 charge. Oxygen is in the group with 6 valence electrons, meaning it's going to take on 2 more, and we're going to end up with a -2 charge. Okay? All right, so these are the ions at play. Now, if I just stuck those two together, this would not be a neutral compound, right? This would be if I just had these two together, that would be an overall charge of +1, right? Think of it as like the positives are beating the negatives here. By how much? By 1, right? So this is not the formula, okay? Because this would mean 1 aluminum, 1 oxygen, or 1 aluminum, 1 oxide. That is not the answer, okay? What we have to do is we have to reason out in what ratio do these ions have to exist, right? What's the smallest whole number ratio, kind of like an empirical formula, okay? Smallest whole number ratio that these ions can exist to have an overall neutrally charged compound, okay? And the answer is that you need at least 2 of these. That would be +6 overall, and then you can counterbalance that by having 3 oxide ions, okay? So what you end up with here is a formula of Al2, right? So 2 of these, and then O3, 3 of these. Note that these numbers here in the formula are not the charges. In fact, they're like the opposite, okay? So the formula would not be Al3O2. Okay, once again, that is incorrect, all right? It's this number here in the formula is telling us how many of each ion there are, not the charge necessarily. Although you can sort of backtrack and determine what the charge would be from the formula and also by looking at the periodic table, right? Okay, and then the last problem here What am I at? 10 minutes? Oh, shoot. Well, it won't be much longer. Okay, we've got the formula lead-4 oxalate. Okay, well, lead-4, that's actually super easy. That's lead, and it tells me that it has a positive 4 charge, right? Because remember, the cation always comes first, anion comes second, so that Roman numeral 4 means, hey, that's got a positive 4 charge. Oxalate is a polyatomic ion. I'm going to take us back to the computer here for just a second. Let me pull up those polyatomic ions. Boom. Okay. The reason I knew to look for oxalate on this polyatomic ion sheet is because this does not end in "ide." Okay? And the fact that it doesn't end in "ide" is a huge clue that says, hey, that right there is one of those special polyatomic ions. Okay? Its formula is C2O4, and this thing here has a -2 charge. Okay, so the oxalate ion has a -2 charge. Okay, well, once again, we have to have an overall electrically neutral compound. So if I just took one of these and one of these together, that would not be electrically neutral, right? The positives would be winning by 2. So what I must need is an additional oxalate. Okay? This then gives me an overall positive charge of 4, an overall negative charge of 4. That looks much better. So my formula then would be this. Pb, just one of them, right? One lead. And then 2 oxalates. How do you write that? C2O4, but I need 2 of them. Well, you might be tempted to do this. You might be tempted to write this, C4O8. Technically, that's not wrong, right? Because there are 2 oxalates there, right? And there's 4 carbons here and 8 oxygens there. But the real way that this is written is by using parentheses and adding that number there. This is a better way of writing it. This shows us that we have 2 oxalate ions with the 1 lead. Okay? So I think I've pretty much covered all of the little nitpicky things that can exist with these naming conventions, naming rules in this video. I hope I have. Once again, yeah, this is not what you would see. It would be using the parentheses here. Your homework assignment for this pretty much entirely covers, my camera's kind of doing that weird jittery thing. Your homework assignment pretty much entirely has problems like this. There may be a few other problems that are slightly different than naming, but it's largely just on this nomenclature. So I think you guys are going to do a great job, and I will see you in class next time.